Good afternoon, everyone. Welcome to the concluding lecture in the series of lectures on field and Galois theory by Adrita. Today, solvability of polynomials will be discussed. Adrita, please start.
Yeah. So, hello everyone. Today we'll be finally discussing the solvability of polynomials. So, in our last lecture, we had seen a theorem where solvability of a polynomial by radicals was equivalent to the solvability of the Galois group. We hadn't proved the theorem, but if we assumed it, we had already shown that the groups Sn for n greater than equal to 5 is not solvable, and hence any polynomial of degree greater than equal to 5 is not solvable. A specific case, so Abel, also called the Abel-Ruffini theorem, because it's not quite clear who had done it first, so it's named after both of them. So they had only proved it for a general quintic. So their theorem was general quintic. So a degree 5 polynomial cannot be solved by radicals. Now this was a very messy proof because at that time Galois theory was not very well developed, and in fact it was just the beginning, and this proof is very messy with a lot of calculations. But we have seen that given the theorem, the proof just does not hold for degree 5. It holds for 5 and any higher polynomial. And we will prove the theorem today. So this theorem, the fundamental assumption that we have is that our fields are of characteristic 0. Okay, so our theorem, let me restate it, was that if K is a field of characteristic 0, then f in Kx is solvable by radicals if and only its Galois group is solvable. So this theorem actually talks about general polynomials, not just its degree. So given a polynomial, if we can obtain its Galois group, we can say whether f is solvable by radicals or not. So this does not tell you that a degree 5 polynomial does not have a radical expansion, radical root expansion, but it also tells you that given a polynomial, you can decide whether you can solve that specific polynomial or not. So for example, we take this. We have the polynomial x to the 5 minus 2. So clearly this is solvable by polynomial, and this has 4 complex roots and 1 real root. And how do we find, now we see this, we would like to prove the theorem. So before proving, we just see how we can do that. So for this specific polynomial, the first step that we do is we add the fifth roots of unity. Okay, so the root will be, say, zeta, which is equal to e to the power 2 pi I by 5, and we extend q to q zeta, and this gives us this expansion. And this is a degree 5 polynomial. We are adding the roots of unity except 1 because 1 is already there. So this extension will give us z modulo z5 cross. So this is the group isomorphic to z modulo 4z. Sorry, 5z. And this is congruent to z modulo 4. So this is our first step. And the second step that we do is we add in all the roots, all the other roots, other required roots. So since we know this polynomial is solvable, we know what is required. That's why I put it in quotes. And in general, we do not know. So the main problem in proving the theorem is to find this required root addition. So we can add the other required roots, which in this case is the fifth root of 2. That is this. And we get this expansion. So we have q zeta, and we have q zeta comma fifth root of 2. And this, as we already said, is z comma 5z cross, and this expansion is z comma 5z. All right, so we can see that this is the Galois group. This is a normal expansion and it's separable. So this is the required Galois group. And so it's called, let's call it G. And G is of order 20. And we can see that this expansion E, which is normal in any group. So E normal in 5z, normal in G. This is a solvable expansion of the group G. So of course we get a solvable expansion, and hence we get that the polynomial is solvable. So we assume the theorem. So if a general polynomial is solvable by radicals, then its Galois group is solvable. And that is the first thing that we proved today. So we proved the first direction. So we have solvable by radicals implies the Galois group is solvable. Okay. First, we do the similar technique as we did in the example. So first, what we do is we add in all roots of unity. Now, we want to know which power we take. So we take some specifically large n. We cannot take more than the degree, but we might take something less than the degree as per our requirement. But we take some specific large enough n. So what we have is we have k, and we have k zeta, and let us say so. Okay, so this is zeta, and we call this to be k1. And clearly this is the splitting field of x to the n minus 1. Now again, this is of degree n minus 1. So we have this expansion, and another point to note is that we do not know what our group K was. A priori, we knew that that was Q, so the expansion had degree 4. So the expansion has exactly degree 4, and we could say that the Galois group was Z modulo 5Z cross. But here we do not know a priori what roots are already present in K. So what we have here is that the Galois group, or the Galois extension, will consist of all automorphisms, which will take zeta to the power j. Let's not use I. So zeta to the power j for some j. And these might not be all the automorphisms. And so what we have is that this group, so this j belongs to Z modulo nz cross. Now this automorphism group need not be the whole group. So the Galois group, that is k zeta over k, is a subgroup of Z modulo nz cross. Now in particular, the important thing to note here is that this is abelian. And that is exactly why we need it, because again, we'll be doing solvability, and we know that abelian groups are solvable. So this solvability will help. So this is our first step. We added in all the roots of unity. Now we move on to our second step. So what we do next is as follows. Okay, so previously what we did, we just added in the roots of 2, and we had exactly one root, so we could add just square root of the fifth root of 2. But so here if we do something similar, we have k1 which is equal to k zeta, then we have k2 which could be say k nth root, uh, uh, it need not be n, so we take j1th root of alpha 1, and we could take k3 equal to k j2th root, sorry, this will be k1, this will be k2 of alpha 2, and so on. But this is not exactly correct in this case, because as we have already seen, the Galois group needs to be normal, and for the group to be normal, the specific requirement is that it is the splitting field, and hence we need to have all the conjugates. We just don't, it's not enough to just have the roots of alpha 1, we need to have the conjugates, the roots of the conjugates as well. So for example, we take this extension, so we have q, and we take q square root of 2. Now this is normal because it's the root of the polynomial x square minus 2. And then we could take the expansion q of square root of 2. But this is not normal. So what exactly is missing here? So instead of just taking this, we need to have the expansion q, which has the square root of 2, and it has the square root of minus root 2. So we need both of these elements to make this into a normal extension. So these are the conjugates. And so this is not correct. What we would like to write here is we include k1, the j1th root of alpha 1, and the j1th root of conjugates. So there need not be just one conjugate, there could be many more. So we just take one and we take all its conjugates and their roots. And similarly, we have here we have k2, we have alpha 2, j2th root, and we have again j2th root of conjugates. Okay, so we have this extension k1, k2, k3 because we need to add as many roots as we want, because we have not said a priori whether our polynomial is irreducible or not. So if it would have been irreducible, one root have been enough. But since it's not specified a priori, we could have as many roots. So for each set of conjugate roots, we get a different extension. So we take one extension and then the other, and then we go on. And since the polynomial is a finite degree, we get a finite number of extensions, and this is not an issue. Now we would like to see the solvability. So we get our extensions, and what we want to see is the following. So we consider, say, the nth roots of alpha and over L. So this is the extension where L contains, so we are looking at k1, so L is our k1, but in general we need to go from one to the other. So let's say we have one and we are going to the next step. So L contains the nth roots of 1. So this is a Galois group. So the so we want to see at the Galois group. So what's the Galois group? So the Galois group here consists of automorphisms which takes the nth roots of alpha to the nth roots of alpha times some zeta to the k, where k is in z mod nz. And so again, by the similar method that we had seen earlier, we can conclude the following. So similar to the above, we can conclude that the Galois group is a subset of z modulo nz, and in particular it's abelian. So we have found an extension such that each extension is normal and we get a chain of it. So what we have is we have k naught, we call that, so we have k which is equal to k naught, then we have the extension k1, k2, and so on up to some km, and each extension, since it's abelian, it's normal. So these are all normal, and it has Galois group abelian. Okay. Now, why is it abelian? Because all the Galois groups are either a subgroup of Z modulo NZ cross, because when we add the first roots of unity, we get this. Sorry, we add the nth roots of unity, we get this, or it is a subgroup of Z modulo GIZ, which is again abelian, and the subgroup of an abelian group is abelian. So we get this chain of fields. And from this chain of fields, we get the chain of groups, which is like this. So we have GM, which is the whole Galois group. Then we have this GM minus 1, GM minus 2. So these are the corresponding groups up to 1, or the trivial group. And we've already seen their normal extensions. So in particular, all of these are normal. And we have seen that when we extend, we get the quotient to be abelian. So in particular, these quotients are abelian. Since we have constructed it specifically in this way, we get all the quotients to be abelian and hence solvable. So we have proved the first part of our theorem, which said that if we have a solution in radicals, we get a solvable expansion. Now we prove the other direction, that is, so we want to prove the other direction, which says the Galois group is solvable, implies that the polynomial is solvable by radicals. All right, so we shall use some methods of, we shall recall some applications of group theory here. So since the Galois group is solvable, we can split the Galois group into Z modulo NIZ, the direct product. So in particular, it is enough to look at Z modulo N. Okay, so we prove a little more general. We prove this direction in a little more generality. So what we have is that this theorem suggests the following problem. Now, what is the problem? The problem says that given this expansion K over M, we have the Galois group Z modulo NZ. So since we've already seen that we can decompose it into this form, we say that we have an extension which has the Galois group Z modulo NZ. Now we want to find what is N. Now in particular, to prove the above theorem, so our query boils down to the following. Is M of the form K times nth root of K for some number A, where A is in K. Now, this is exactly what we want to prove. And instead of just assuming characteristic 0, we shall assume something more. And we shall show this theorem in a little more general setup, as said. So we make the following assumptions. So we have 3 assumptions. So first is that K contains all roots of 1. And this is as earlier, so all nth roots of 1. So as earlier, we required the nth roots to be there so that we can take the conjugation action and look at the automorphism group properly. So priori, we assume that K contains all the nth roots. Second, we assume that characteristic of K does not divide N. And third, we assume that N is prime. Now we know again by the characterization of abelian groups that any abelian group can be boiled down to writing it as a direct product of the primes and their powers. So we can assume without loss of generality that n is prime, and if not, we can just go ahead with non-primes. But later on we will require at some point to change it to a prime. So we assume a priori that n is a prime. Now our main question is how to find this k. So because if we find the same, we are done. Since we already know that the expansion is of the form Galois group is of the form z modulo nz, and m is the Galois extension. The Galois extension of k. So if m is of the form k root over n times root over n of a, we know that k is a radical extension, and since it's a radical extension and it is the Galois group of some polynomial, this polynomial is solvable by radicals. So all we are left to do is find such an a. Now, how do we do that? We do the following. Now, the question is how to find A. So, suppose the Galois group is generated by sigma, and we already know that the Galois group is z over nz. So, sigma to the power n is 1. And if such an A exists, then we have the roots of xn equal to A, which are nth root of A, then zeta times nth root of A, zeta square times nth root of A, and so on up to zeta to the power n minus 1 times the nth root of A. And where this zeta is zeta to the power n is 1, and it's a primitive root. So primitive root in particular is that zeta generates all the roots. So in particular, we can take the first roots of unity. The nth root of unity such that the power is 1, and this gives us the roots. And if such an A exists, we have all the roots in the group M. In the field M, and we have sigma of square root n A. This takes it to say zeta. Say it takes it to one of the roots, and so for without loss of generality, we may assume that it takes it to zeta times. Now, instead of looking at M as a field, we make a little more general assumption. We look at M as a vector space over K, and this setup makes sigma a linear transformation from M to M, of course. Now, if we assume this setup, we can clearly see the following. So this gives us the following. So root n alpha, so root n A is an eigenvector with eigenvalue zeta. So because we already saw that sigma of root n alpha is equal to zeta times root n alpha. So this clearly says that this is the eigenvalue and eigenvector. And so if such an A exists, we need to look at eigenvalues and their corresponding eigenvectors. And to find such an A, if we can find all the corresponding eigenvectors, we can get back such an A, and hence we can say that it is indeed a group. So M is indeed a group of the form K times root n A. So we look for eigenvectors of sigma on M, where sigma to the power n is 1. And therefore, all possible eigenvalues are 1, zeta, zeta square, and so on. Now there is a slight problem here. That is, do enough eigenvectors exist? As we've already seen in our linear algebra course, that eigenvectors, so we need not have enough eigenvectors which span the whole set orthogonally. So in particular, this question is equivalent to asking, is sigma diagonalized? As it turns out, the answer is yes. And here we need the following. So yes, when zeta is in K, we assumed by the first assumption, we know that K has all the roots of unity. So in particular, zeta is in K, and we have characteristic of K does not divide N. So if we have these two assumptions, the matrix of sigma is always diagonalized. So we see the following proof. So before doing it in generality, we see the proof for n equal to 3. In this case, we take some v in M, and we already know that the eigenvectors are zeta to the power I for some I. And in this case, we have the eigenvectors 1, omega, and omega square. So, sorry, these are the eigenvalues. And we want to find if the eigenvectors span all of them. And so in particular, we want to write v in terms of the eigenvectors. So what we do, we look at the following. So you look at the vector v plus sigma v plus sigma square v. Now this is fixed by sigma. Then we look at v plus omega sigma v plus omega square sigma square v. This has eigenvalue omega inverse, or which is also equal to omega square. And finally, we have v plus omega square sigma v plus omega sigma square v. And this has eigenvalue omega. We have these three expansions. And in particular, if we sum them up, we get 3v because 1 plus omega square is 0. So taking the sum, we get 3v, and this implies that v is 1/3 times the sum of 3 eigen vectors. And hence we can write v as v is in the span of the eigenvectors, and hence we get the whole space. So here we notice that we required the characteristic of K does not divide N for the fact that we can take 1/3 here, and we needed zeta to be in K so that we could write this expansion, which already belongs in K. Okay, so we get the following. From here we can write any v in M can be written as the sum of eigenvectors, and this implies that sigma is diagonalizable. Okay, now we come back to the general. So this was the case for 3. So in general, what we can do is for general n, we do the following. We take v plus sigma square v up to sigma to the power n minus 1v, and then we take v plus zeta sigma v plus zeta square v, so on. Then we get zeta square sigma v, zeta 4 sigma square v, and so on. We take the sum, and then we can again write v in terms of the eigenvectors, and hence we can prove it for any general n, and for any sigma it's diagonalizable for any n. Okay, so next we do this. So we have already seen that it is diagonalizable, and we have enough, and so the main aim was to have enough eigenvectors. So we already have enough eigenvectors, and now we proceed as follows. So we pick an eigenvector with eigenvalue not equal to 1, because we want to have a general, so we want to have a map which is not the identity map. So we have, say, sigma of t is equal to zeta t, and sorry, zeta times t, and in particular this implies that sigma of t to the n is equal to t to the n, and this says that t to the n is in K. Now we're looking at it not only as a vector space, we're looking at it as a field. So since sigma of t to the n goes to t to the n, it is in the fixed field, and the fixed field is K here, and so we get t to the n is in K. Therefore, we can conclude that m is equal to K of nth root of t, and this t is our required A, and hence we are done here. So we can summarize as follows. What we have done till now, if K subgroup of M is Galois with Z modulo NZ as the Galois group, such that we had the following conditions. K has nth roots of unity, and characteristic of K does not divide n where n is a prime. Then M is K nth roots of A for some A. And we are mostly done. But again, the question is, when we have two different expansions, so there, suppose there exists two numbers A and B, such that we can write it in this way. So what about that? Before coming to that, let us look at an example. How do we apply it? So for example, we take the polynomial x cube plus x square minus 2x minus 1 equal to 0. And this polynomial, it's easy to check, has the roots. So we have alpha 1, which is equal to 2 cos 2 pi by 7, alpha 2, which is equal to 2 cos 4 pi by 7, and alpha 3, which is equal to 2 cos 6 pi by 7. Taking these three roots, we get this cubic, and clearly the Galois group is Z modulo 3Z, and it's generated by sigma, which takes alpha 1 to alpha 2 to alpha 3 to alpha 1. So it's generated by this simple cycle. And what we want to do now is we want to generate the eigenvectors, get the Galois group in terms of radicals, and then finally find the roots. We already know the roots here, and so the main goal is to find the root, but in this case we already know the root, so we want to see how we can generate the group so we can get the roots. So first we could solve this equation by taking the seventh roots of 1, because we already see that it's cos 2 pi by 7 in general. But here, when we want to construct the group in this manner, what we do is we want to generate the roots by taking third root. So instead of taking seventh roots, we want third roots because the degree of the polynomial is 3. So we find the eigenvectors. So what we do, again, we do the similar technique. So we have alpha 1 plus alpha 2 plus alpha 3 equal to minus 1. Then we have alpha 1 plus omega alpha 2 plus omega square alpha 3. Alpha 1 plus omega square alpha 1 plus omega alpha 3. Now, we could just calculate them. But using just the coefficients of the polynomial, we can just check that the cubes are in q omega. So just taking the cubes of all the, so this cube is -1, which is obviously in q, and the other two cubes, they turn out to be, so cube of the first equation is -1, cube of the second equation is 21 omega plus 40, cube of the third equation is 21 omega bar plus 40. So we have these three cubes, and where of course omega is -12 plus root 3 I by 2. And these three cubes are there, so we get a cubic. And in general, we can write these three as cube roots of elements in K. And so we can write our alpha 1 in this manner. We get alpha 1 is equal to 1/3 -1 plus the cube root of 21 omega plus 14 plus the cube root of 21 omega bar plus 14. So we get our alpha 1 in this way. A priori, if we do not know the roots, we can just calculate it in this manner. So finding the eigenvalues and then the eigenvectors and then writing them in terms of the eigenvectors, we can find alpha 1, and then using simple linear algebra, we can find alpha 2 and alpha 3 as well. Now, let's get back to the question that we saw previously. So our question was, when is k times nth root of a equal to k times nth root of b? And again, just for recall, we know this is an eigenvector of sigma with eigenvalue say zeta, and this, so nth root of b is an eigenvector of sigma with eigenvalue zeta to the power j for some j. Now what we can do is we can raise b to some power such that the eigenvalue becomes zeta. So since zeta is a generator, if we can raise it to some power, we can get back zeta instead of zeta to the power j, and hence we can assume nth root of a and nth root of p have the same eigenvalues. So same eigenvalues is zeta. And this will imply that the nth root of a divided by the nth root of b is fixed by sigma, because then the eigenvectors will get, eigenvalues will get cancelled, and this will have eigenvalue 1, and hence it is fixed. And so this is in K. And in particular, this will imply that k nth root of a is equal to k nth root of b. So we have already answered our question. So our question is, so the answer is that if two elements have the same eigenvalues, then they generate the same group. Again, we have shown that given any two vectors, we can raise them to such a power as that they have same eigenvalues. So this group that we generate, so this field that we generate is always the same. So that's it for the solvability. Now we have finished the proof of the theorem, and we have already seen that any power greater for polynomial with power greater than equal to 5, the polynomials are not solvable. Now we would like to apply this theorem, the theorem of solvability, to see the polynomials of degree 2, 3, and 4. First, we look at quadratics. We already know the simple formula for quadratics, but anyways, we would like to look at it again. So we have this x squared plus bx plus c equal to 0. and suppose it has roots alpha and beta, then of course sigma alpha is equal to beta and sigma beta is equal to alpha. And clearly the eigenvalue, since it's just the second roots, so the eigenvalue of sigma is -1. It cannot be 1, otherwise it's again the simple identity map. So the sigma eigenvalue of sigma is -1, and the eigen vector, easy to check, is alpha minus beta, because it takes alpha to beta and beta to alpha. So alpha minus beta goes to beta minus alpha. So the eigenvector is alpha minus beta. And from simple quadratic manipulation, we can see that alpha minus beta squared, this belongs to K because it's alpha squared plus beta squared minus 2 alpha beta, which is again alpha plus beta squared minus 4 alpha beta, and all of these belong to K, and hence the sum belongs to K. And it's easy to check that this is equal to b squared minus 4ac divided by a squared. Okay, and a plus alpha plus beta, this is equal to minus b by a. This again belongs to K, and so we can write alpha and beta in terms of these elements, and we already know Sridharacharya's formula, and that yields the radical expansion. So the next thing is cubics. Now it turns out that in the case of cubics, we have a little more complicated expansions and calculations than the quadratic. So though the quadratic equation was developed quite early, it took quite some time to develop cubics. And as it turns out, after cubics, the solvability of quadratics is, solvability of quartics, so degree 4 polynomials, is not that difficult, because the solvability of a 4-degree polynomial eventually boils down to solving a 3rd-degree polynomial, which if we can do, is quite easy. As in, the solvability of cubics needs to be developed for that. So we have this polynomial x cubed plus bx plus c equal to 0. Note that I have omitted the 2nd-degree term, so we can always get rid of the 2nd-degree term by using a substitution of the form x equal to t minus b by 3a. So if you have a general cubic, so if the cubic is of the form ax cubed plus b x squared plus cx plus d equal to 0, then we can substitute this and we can omit the square term, and we can get this simpler expansion. So we get the roots, say alpha, beta, and gamma, and clearly the Galois group is a subgroup of S3. And without loss of generality, we can just say it is equal to S3. And we have already seen the following solvable expansion of S3. So we have 1, A3, and S3. And the first, so the solvable group expansion is 1. And we have, so we had the first quotient is Z modulo 3Z. And the second expansion is Z modulo 2Z. So these 3 quotients, and this is a solvable expansion with these groups. So we have the final following expansion of fields. So we already have A, alpha, beta, gamma. And then we have some group F, which we want to find, and then we have K. And so if this is a root 2 expansion, and this is, so first we take a square root and then we take a cube. So what we want to find is this field F. F is generated by some element fixed by E3. And in particular, S3 over E3, this acts on it as -1. So on the element that generates F. And in particular, let us say delta to be alpha minus beta, beta minus gamma, gamma minus alpha. So we can see that -1 acts on this, and in particular we can take gamma square, which is equal to alpha minus beta square, beta minus gamma square, gamma minus alpha square, and doing some calculations using the coefficients, this turns out to be -4b cube minus 27c square. And again, we are finally boiled down to finding the Eigen Vectors. So, okay, so we see that this belongs to K. So we can see that F is equal to, F is equal to K times delta, because you can just take the square root and this is a square expansion. So we get this. Now we want to go from F to K alpha beta gamma. How will we do that? We do the following. So we again take the eigenvector expansion. So alpha plus beta plus gamma, and this is equal to 0. Since the square term is 0, then we have alpha plus omega square beta plus gamma, plus omega gamma, and then we have alpha plus omega beta plus omega square gamma, and these are the eigenvectors of sigma. And what does sigma do? Sigma takes alpha to beta to gamma to alpha. So we get the following expansion. Now, finally, what we have here will be this. So we have, let us call these. So let's give these some names. So we have, say this is y and this is z. So 0 is in k delta. So 0, y, z. These are in k delta, all three of them. And this will give y cube, which is equal to minus 20 c divided by 2 plus 3 root 3 I by 2 delta, and z cube equal to minus 27 c by 2 minus 3 root 3 2 delta, and hence we get alpha equal to y plus z by 3. And this gives us the expansion for the cubics. And let us look at an example. So we have x cube plus x plus 1 equal to 0. And again, using the expansions, we have the following. So 4b cube minus 27c square. So this is delta square. This is equal to minus 31. And hence delta equal to root minus 31. And y we get as cube root of minus 27 by 2 minus 3 root 3i minus times root under minus 1 by 2, and z is equal to plus 3 root 3i root minus 31 by 2. And this gives us the solution. So taking alpha equal to y plus z, we get the solution of this polynomial, and this turns out approximately to be minus 0.68. So we can do this for cubics. And now finally, let us look at quartics. Again, we can write a quartic as follows. We have x4 plus ax square plus bx plus c. This is equal to 0. Again, we can do a substitution and remove the cubic term. So we do the following. We have this solvable expansion 1. Then we have the Klein 2 group. So z mod 2z square, which is in A4, which is in S. So this was our solvable expansion. And this is clearly Abelian. Then we have this, which is z mod 3z. And finally, we have z mod 2z. We have this following solvable expansion. And we have this. We have k, alpha, beta, gamma, delta. Then we have f2, f3, f1, and finally we have k. So we do a square root, a cube root, and finally all square roots to get these following expansions. So in particular, we can say that k is generated by the permutations 1, 2, 3, 4 and 1, 3, 2, 4. So they give this group and then they generate K. So, so again, we would like to look at the eigenvectors, which turn out to be the following. So we get the eigenvectors as follows. If the four roots are, say, alpha, alpha, beta, gamma, delta. So we have alpha plus beta minus gamma minus delta. We have alpha minus beta plus gamma minus delta, alpha minus beta minus gamma minus delta, and finally we can write the sum of all four, which is already 0. And we have two vectors 1, 2, 3, 4 and 1, 3, 2, 4. And these have eigenvalues 1 minus 1 minus 1, 1 again minus 1, 1, 1. And if we sum these by 4, sum these 4 and divide it by 4, we get alpha. And then we can do the simple linear equations calculations and find the other three. And in particular, if we take the squares, alpha plus beta plus gamma plus delta square, alpha plus beta minus gamma minus delta square, alpha minus beta gamma minus delta square, and alpha minus beta minus gamma minus delta square. So taking all, sorry, this should be a plus. So taking all these four squares, these are permuted by S. Now in particular, this is 0. So we only have these three numbers, and taking these three numbers, these are the three roots of a cubic with coefficients in K. So these are roots of a cubic with coefficients in K. And we are again boiled down to solving a cube. So the main observation here is S4 factors through S3. And the S3 groups comes in this extension here. So when we look at the quotient of these two, we get S3. And so we find F1 and we are boiled down to solving a cubic. And since we already know how to solve a cubic, we can solve it in this manner. And so that's it for today. Thank you. Are there any questions?
I don't think there are any questions. Thank you, Adrita.
Thank you, Adrita. You have done a great job.
Thank you, sir.
Thank you, Adrita.
Yeah, thank you, everybody. Thanks for attending the talk. I had great fun giving the talks. So hope to see you soon.